Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the lecture 7 of this course. In the last lecture we have discussed about standard atmosphere, where we have derived the relations of pressure, temperature and density with geopotential altitude. And as discussed, that today we'll be discussing, or even rather simulating, that pressure, temperature and density in MATLAB. Alright, so this is how the MATLAB looks like. I've already written one code for related to aerodynamic center, calculation of aerodynamic center and center of pressure. Now let us write the MATLAB code for finding the pressure, temperature and density with geopotential altitude. So I always suggest my students to hone your skills in simulation as well, which is quite useful. Now let me just start writing. What we'll do is we'll ask the user to enter the geopotential altitude in meters. Okay, so let me just write here double comment. Last time we used 1 percentile. So this model will be is atmospheric model. Atmospheric model. Alright, now let me begin this with as a function file. Alright, now if you want to learn the commands here in the command prompt, you just have to mention help and the command that you want to learn about. Okay, so help function. So you'll get a complete documentation related to function file. Okay, so this function declares function name, inputs and outputs. So this MATLAB function declares a function named myfun, depending upon the name of the function that you have written, that accepts inputs x1 to xm and returns outputs y1 to yn. So you can enter n number of inputs and we can get y number of outputs. Alright. Similarly, you can find here, you can input CLC, you can put help and write the command name. Okay. Now let me write the function file name here. Function file name I have written here as std.atm, standard atmosphere. So the name of the function file and the name of the .m file should be same. Okay, that is the condition. Alright, so let me write here std exactly as the name of the file, atm. Okay, and I'll mention here 2 brackets to mention the amount of the inputs that we will be entering here. Okay, so now we'll be asking the user, please prompt the user for geopotential altitude. Okay, h equals to, for that the command is input, h equals to input brackets. Okay, enter the geopotential altitude, enter the geopotential altitude in meters. Okay, fine, 0 to 25,000 meters, 0 to 25,000 meters. Okay, and in the end semicolon. Fine. Now what are the variables that are available to us? So that we'll be writing now. Okay, now g naught, let me write g naught equals to 9.81, that we know this is the gravity at mean sea level in meters per second square. Alright, next universal gas constant R equals to 287 joules per kg Kelvin. Okay. So this is the specific gas constant for air, joules per kg Kelvin. Next is the pressure at sea level, that I am denoting it as P naught, equals to 1.01325 into 10 to the power 5. So we write e to the power 5. Okay. This is the pressure at mean sea level in newtons per meter square. Next is density, rho naught equals to 1.225 kilogram per meter cube. Okay, this is the density at mean sea level in kilogram per meter cube. What else do we know? Yes, temperature at sea level. Temperature at sea level is 288.16 Kelvin. Alright, temperature at mean sea level is 288.16 Kelvin. Now, next thing is we have to determine which layer. Alright, determine. Let me put a space over here so that looks good. Determine which layer the altitude falls into. Okay. Which layer the altitude falls into. So when the user enters this information, so with this code, MATLAB will realize that this altitude is coming in at isothermal layer or the gradient layer. So now we'll put condition. Alright. If h is greater than or equals to 0 and h is less than or equals to 11,000 meters, alright, then we'll be following the gradient layer. Let me write here the comment as gradient layer, which comes under troposphere. Alright. So now here h1 is the sea level. Let me write here h1 equals to 0. Alright. The lapse rate is, I have already mentioned in the previous lecture. Let me write it here. Minus 6.5 to 10 to the power minus 3. E to the power minus 3. Okay, so this is the lapse rate in Kelvin per meters. So let me write here it as in the one line. Alright. Okay. Next is change in the altitude. So I'm writing here as del underscore h, change in the altitude, equals to h. H has already been entered by the user. Okay. So h minus h1. You can notice here I am even the space MATLAB recognizes. I can enter minus here, or even entering after space I can enter minus over here. Okay. So just for it to look good, I am entering space over here. So del h equals to h minus h1. Next is the temperature. So T naught we already know. Now we need to find temperature. That was, the expression was T naught plus A into delta H. A into delta H. So delta H we have mentioned here, del H. Alright. Okay. Now next is, now we found the temperature. Next we have to find the pressure. Okay. Pressure equals to P naught. The P naught we have mentioned already. So you can see here, after writing here, it is highlighting with this color. Okay. So P naught is mentioned already. So P naught into T upon T naught. Remember the expression that we have derived extensively in the last lecture. So I'm just writing those expressions here. So P naught into T upon T naught power. Let me write the expressions here. Alright. One more brackets, minus G naught by AR, minus G naught by AR, A into R, minus G naught by AR, minus 1. Okay. Minus 1. Let me write here semicolon. Alright. Similarly, we have to find density. Okay. Rho equals to rho naught into T upon T naught power minus G naught by AR minus 1. So this is same. So let me write here. Okay. Rho naught into T upon T naught power minus G naught by AR minus 1. So this is the density. So now for first condition is fulfilled. Now we will be writing the next condition, that is isothermal layer. Okay. Else if H is greater than 11,000 meters and H is less than or equals to 25,000 meters. Okay. So then what were those equations? And this layer is actually isothermal layer. Okay. Here we write H1. Here the base altitude will be 11,000 meters. Alright. 11,000 meters. Del H will be H minus H1. Okay, that will remain same. H minus H1. Okay, so you have to rewrite del H, even though del H we have written here, but MATLAB will, after recognizing that if it is a isothermal layer, it will directly switch to else if statement. Okay, so that is why we are writing again. Del H equals to H minus H1. Now what is the temperature? Yes, temperature is constant, that is 216.66 Kelvin. Alright, what is the pressure? At 11, that is also known to us. So I am writing here at a pressure at 11 kilometers. That is around 22,615.57. Okay. This is the pressure at 11,000 meters. You can check from the tables as well. Next, density underscore 11 equals to 0.3636 kilogram per meter cube. Alright. Next is pressure, of course, P equals to P11. P equals to P11 into E to the power. Alright. Remember the expressions. The minus G naught into delta H minus G naught into delta H minus G naught into delta H by RT. R into T. Alright. Then we have density. Rho equals to rho 11 into E to the power minus G naught delta H into RT. Alright. Okay. Now we have found the pressure and as well as density. Next statement would be else if the user has entered geopotential altitude beyond 25,000 meters. So then we will mention display altitude out of supported range. Out of supported range, that is 0 to 25,000 meters. 25,000 meters, full stop. Alright. Then return. And finally we end the statement. Alright. Now let me also display the results over here. Display the results. I would like to print these statements. So fprint, for that command is fprintf. Let me write here, and this is the colon apostrophe. I want to write in a new line. I am written here /n. So atmospheric properties. Atmospheric properties at whatever the value that user has entered. Let me write here as percentile 0.2f in meters. Now what is 0.2f? It prints 2 digits after decimal. Alright. So you have to explore this, what I am writing over here. So 0.2f m meters, geopotential, altitude. Geopotential altitude. Okay, then again /new line and close, and then we have to tell what is the altitude value that we want MATLAB to print, that is the altitude. Okay, next fprintf, again the same. Now I will be writing the temperature. Temperature T, again percentile 0.2f, 0.2f. The temperature is in Kelvin, and again new line. Alright, comma. So what is the value? T. Alright, okay, this is semicolon over here. Similarly, temperature we are done. Next write pressure. Pressure is, it is P, percentile 0.2f. So this is Newton per meter square. Alright, Newton per meter square, not in kelvins. Okay, so this is pressure. And finally density. Alright, density, right here rho. So density, let me take it till 4 decimals. 0.42f, kilogram per meter cube, kilogram per meter cube, new line, and what is the value? Rho. Alright, now let us end the function file. Okay, now this is end is for the function file. So let me save this. So now we are in a position to run this code, where the MATLAB will ask us, prompt us, enter the geopotential altitude in meters. Alright, so I have saved this code, and let me here run this code. Here we have the run button. Alright, unrecognized function or variable input. So let me write here input. Alright, okay, run this code. Now see here, MATLAB is prompting us, enter the geopotential altitude in meters, 0 to 25,000 meters. So let me enter 10,000 meters. Okay, so 10 kilometers. Alright. Okay, and then we have another error here, printf. Alright, let me write here print. Let me run the code again. Let me write 10,000 meters. Alright, so now finally we have the atmospheric properties at 10,000 meters. The temperature is 223.16 Kelvin. This is the pressure, and this is the density. Alright, so now let us run the code and again to find the pressure, temperature, density at the isothermal layer. Okay, Let me write here 20,000 meters. Okay. Now this is temperature will remain constant, that is 200 Kelvin, and this is the value of pressure and density. Okay, Newton per meter square, kilogram per meter cube. Now finally, let me enter the value. First of all, let me clear this MATLAB prompt command window. Now let me run this code and let me enter some random value beyond 25,000. Okay, so let me enter 30,000, say for example. And now we have prompt, that is altitude out of supported range. Okay, that is what we have mentioned over here, altitude out of supported range. All right, so this is how we can actually find pressure, temperature and density at standard using the standard atmospheric values. And please remember, these equations are only applicable till isothermal layer, that is 25 kilometers. All right, so beyond that, these expressions, they do not hold any valid. All right, so now that we are done with this standard atmosphere, now we can begin with our equations of motion, that is equations of motion of steady level flight. All right, now let us go back to our slide. Let us begin with the equations of motion. All right, so let me draw a free body diagram over here for the equations of motion of the aircraft. All right, and this is the velocity. So this is the direction where the aircraft is going. Okay, and this is with, let me draw the chord line first. Okay, and we'll assume there is an offset to the thrust. This is capital T, offset to the thrust by angle epsilon. Okay, now the lift vector, we know with this will be perpendicular to the velocity. Okay, so let me write the lift vector over here. So this is lift vector, and this is the weight of the aircraft in the downward direction. All right, all right. Now where is the angle of attack? The angle of attack here is the angle between the chord line and the velocity. Okay, so this is the angle of attack, alpha. All right, now the drag will be opposite to the velocity. All right, drag will be the opposite to the velocity, and this is the local horizontal. Local horizontal. Okay, now let me define few other angles here, the direction in which the aircraft is going. Okay, the direction in which the aircraft is going is represented by this angle. This is gamma. Okay, the angle between the velocity and the horizontal, and the orientation of the aircraft is represented by this total angle, alpha plus gamma. Okay, so that is represented by capital theta. All right, okay, so let me write down few points over here so that it becomes easy for you to comprehend. So here we have lift L is perpendicular to flight path direction. Drag D is parallel to flight path direction. Alright, weight will be acting vertically downwards. W weight acts vertically downwards towards center of the earth. And finally, we have assumed the thrust T is acting at an offset of epsilon with velocity. Alright, okay. Now I have entered a new term over here, that flight path angle gamma. So now if this is flight path angle gamma, then what will be this angle? This will also be flight path angle gamma. This will also be flight path angle gamma, and this will also be flight path angle gamma. So since gamma is the flight path angle, let me write down its definition. Flight path angle okay. So what is this flight path angle? Angle between the velocity vector of aircraft. You can also mention here direction of motion, whichever direction the aircraft is moving. Direction of motion, that is of course in the absence of wind. Alright. So angle between the velocity vector of the aircraft, the direction of motion, and the local horizontal. So it shows whether aircraft is climbing, descending, or level. Alright. So when gamma is equals to 0, so that means the aircraft is cruising or level flight. Okay. So when gamma is greater than 0, that means aircraft is climbing. And when gamma is less than 0, and obviously it is descending or landing. Alright. So this is the flight path angle gamma, angle between the velocity vector and the local horizontal. Okay. In the absence of wind, please remember whichever direction of the velocity is, aircraft is moving in that direction. Alright. And this is defined by the flight path angle gamma. Next, I have taken new name of pitch angle over here, that is theta. Let me define what is this. Pitch angle theta. So this is the angle between aircraft's longitudinal axis Now which is longitudinal axis? The line joining from nose to tail. Alright. From nose to tail. That is the longitudinal axis. So the angle between aircraft's longitudinal axis and the local horizontal. Alright. So it indicates aircraft's nose up So it indicates aircraft's nose up or nose down attitude. Alright, or nose down attitude. So we in aircraft terminology we call it as attitude. Okay. So positive theta means what? So if we have positive theta, that is nose is pointing upwards. Alright. And while negative theta will point, nose is pointing downwards. Alright. So now this figure we can easily write this theta is equals to alpha plus gamma. Okay. So theta is equals to alpha plus gamma. Alright. Now when gamma is 0, that means during level flight, the theta will be exactly equals to alpha. Alright. The theta will be exactly equals to alpha. Now these were the definitions of flight path angle gamma and the aircraft pitch angle. Now coming to these equations of motion, now we know that aircraft generally moves in a curved path. Even though aircraft looks like it is going in a straight and level flight with respect to ground, but it is still executing a curved path, flight path, when compared with the radius of curvature. Okay, so it is still executing a curved path with radius of curvature, which is equal to the absolute altitude. Alright. So now we know when an aircraft moves in a curved path, the motion is known as curvilinear motion. Okay. Curvilinear motion. Okay. And when an object moves along a straight line, then the motion is known as rectilinear motion. Okay. So now we will be applying Newton's law. So that is Newton's law is F equals to ma. Okay, so this holds for both the cases. Newton's law holds for curvilinear motion. It also holds for the rectilinear motion. Alright. Now, since the aircraft is moving in a curved path, so we will be considering curvilinear motion. Consider curvilinear motion. Alright, so where we have two mutually perpendicular axes, one is along the direction of flight path, one is along the direction of flight path, and other is obviously normal to the flight path. Other is normal to the flight path. Okay, so now we'll be applying Newton's law along the flight path. That is, what are the forces which are acting parallel? Okay, so F equals to ma. Here we have m into a. Here acceleration we can mention m into dv upon dt. Alright, so here a equals to dv upon dt. This is the acceleration along flight path. Alright, so now we'll be saying now what are the forces which are acting parallel to the flight path. Okay, now let us go to the figure again. Now if you see this figure and try to resolve the components, now first we'll be seeing the forces which are acting parallel to this velocity. Now let us first focus on thrust. Alright, the thrust is an offset of epsilon over here. So with velocity, here we have thrust will be t cos epsilon in this velocity direction, t cos epsilon, and it will be t sin epsilon when consider perpendicular. Alright, it will be T sine epsilon. So here we'll have T sine epsilon. Okay, so let me write here first. So T cos epsilon. What about drag? Drag is exactly opposite to the velocity. So we can easily mention here minus D. Minus D. What about weight? So weight here is, this is W cos gamma, and here we have W sine gamma. Alright. So this is also opposite to velocity. So here we'll be having minus W sine gamma equals to m dv upon dt. Let me consider this as equation number 1. Now applying Newton's law perpendicular to flight path. Alright, so summation of forces perpendicular to flight path, mass into acceleration. So here this acceleration will be equals to v square upon r. Okay, so here this is the acceleration normal to the curved path with radius of curvature, for example r. So this mv square upon r is actually centrifugal force. Alright, so A equals to v square upon r is the acceleration normal to curved path with radius of curvature, say r. Okay, and mv square upon r is actually a centrifugal force. Alright, now I can write summation of all the forces perpendicular. Now we'll go back to the figure again. The perpendicular is T sine epsilon, in this here T sine epsilon, that will be positive. T sine epsilon. Lift is already acting in the upward direction, that is plus L. Plus L. What about weight? Weight is acting downwards in negative direction. We have minus W cos gamma. So this equals to mv square upon r. Alright, so now we have these two equations, summation parallel to forces T cos epsilon minus D minus W sine gamma equals to m dv upon dt, and perpendicular forces are, summation of perpendicular forces are T sine epsilon plus L minus W cos gamma equals to mv square upon r. Now these are the equations 1 and 2 are the equations of motion. For an airplane in, or for an aircraft in translation flight only. We are not considering any motions or rolling motion. Okay, rotational motion. We are considering only translation motion. Translation flight. Okay, now we'll be taking some assumptions to make these equations look similar. For example, steady level flight, how these equations looks when we are flying in a steady level flight. So we will be considering static performance. Alright, so static performance leads to reasonable calculation of maximum velocity, maximum rate of climb. Now what is rate of climb? We will also be having a look at it. What is the maximum range, the maximum distance, horizontal distance the aircraft can travel. Okay, so things like that. And static means it is an unaccelerated flight. unaccelerated flight. That means acceleration we will consider as 0. Okay. Also we'll be considering level flight. Here we have again gamma equals to 0. Okay. So now we have considered few assumptions here for static performance, that is acceleration is 0. In level flight we have gamma equals to 0. Okay. So now equations 1 and 2 can be written as equations 1 and 2 can be written as T cos epsilon minus D equals to 0. So here we get T cos epsilon equals to D, and the second equation reduces to T sin epsilon plus L minus W equals to 0. So this becomes L plus T sin epsilon equals to W. Alright. So practically speaking, this epsilon is actually a small number. Practically speaking, the thrust was actually aligned or offset by an angle epsilon with respect to velocity. But practically speaking, this offset is actually a small number, which is approximately epsilon less than 5 degrees. Okay. So now if this epsilon is a small number, so that means cos epsilon will be approximately equals to 1 and sin epsilon will be approximately equals to 0. Now these equations can be further written as T cos epsilon equals to D. You will get thrust equals to drag and lift equals to W. So these are the equations for level unaccelerated flight. Alright. So remember, this we have already discussed in one of the previous lectures, where we have drawn the free body diagram of a aircraft. Here we have shown this is the thrust, we have shown here this is the drag, and this is the lift, and this is the weight. Okay, so intuitively also we could tell the thrust in equilibrium flight, the thrust is equals to drag and lift is equals to weight. Okay, and we also discussed about the point over which it is acting. It is acting at the aerodynamic center when we also consider moments about those points. Alright, so this thrust equals to drag, lift equals to weight. This is the equation for steady level flight, which was quite intuitive also, and now we have derived it using our equations of motion. Alright, so now in a steady level flight we are interested in what is the thrust, thrust required. Let me write here thrust required, it is TR, to maintain this level of flight. Okay, for maintaining this level unaccelerated flight, what will be the thrust required to sustain that flight? Okay, so next we'll be studying thrust required. Alright, and the next topic is thrust required for level unaccelerated flight. Thrust required for level unaccelerated flight. So to sustain straight and level flight, the airplane's power plant, the engine we also call it as power plant. This is nothing, it can be turbojet engine, a reciprocating engine, piston reciprocating engine, or propeller combination. Alright, they must produce a net thrust. They must produce net thrust which should be equals to drag. Alright, so this must be equals to drag. Okay, so now let me write here thrust required equals to drag. Okay, remember what was the equation for drag? CD equals to D upon QS, and drag was QS CD. Okay, and drag is QS CD. All right, and here we also have another condition, that is lift equals to weight. So what was lift? CL was L upon QS. All right, and L equals to QS CL. Okay, so we'll write here lift equals to weight equals to QS CL. Okay, so normally we also write in this way. So thrust required equals to QS CD, W equals to QS CL. We just divide these equations. So what we get is thrust required by W equals to CD upon CL. And what will be the thrust required given the weight? Okay, the thrust required will be W upon CL by CD. Okay, or W upon L upon D. Okay, so this will be the thrust required for maintaining straight and level flight, unaccelerated level flight. L equals to W, thrust equals to drag. So thrust required given the weight, you can easily find thrust required equals to W upon L upon D. So this L upon D is actually called as aerodynamic efficiency. Okay, this is purely related with the aerodynamics of the aircraft. Okay, so now this is the thrust required for an aircraft to fly at a given velocity in level unaccelerated flight. Okay, so we have at given velocity. All right, so let me repeat. So this is the thrust required for an aircraft to fly at a given velocity in level unaccelerated flight. So please do not forget, this is applicable for level unaccelerated flight. And now, as an engineer, we would like to know what will be the thrust required minimum to maintain lift equals to weight. So let me write here. We are interested in finding minimum thrust required to maintain lift equals to weight. Okay, so then now we are talking about minimum condition. Now let us write this equation again. Thrust required minimum will be W upon L by D max. Alright, so thrust required minimum is W by L upon W by L by D max. You can also plot the curve between L by D versus alpha. So it more or less looks like CL versus alpha curve. Okay, so here also we have L by D max. This is L by D max. Okay, so here L by D is again a function of alpha. Okay, so this is a function of alpha. Remember, CL was CL naught plus CL alpha into alpha. Then what was CD? CD was CD naught plus KCL square. So our given aircraft, CD naught will be constant, K is constant. So CD is a function of CL, and CL in turn is a function of angle of attack alpha. Okay, so now for conventional subsonic aircrafts, so this alpha at which L by D is maximum. Okay, so this alpha at which L by D is maximum it is from 2 degrees to 5 degrees. Alright. 2 degrees to 5 degrees. Okay. So whenever aircraft is flying at a velocity for which thrust required is minimum, it is simultaneously flying at an angle of attack at which L by D is maximum. Okay. So let me write here so that you can make a note of it. Hence, when aircraft is flying at a velocity for minimum thrust required, okay, so that means it is simultaneously flying at alpha at which L by D is maximum. Okay, so remember this, if the aircraft is flying at thrust required minimum, so that means it is flying at L by D maximum. That means it is flying at a velocity at which it is having an angle of attack where we have L by D is maximum. So now let me draw a curve thrust required with the velocity. So we'll be working on this curve again and again. Let me give you a brief idea how this actually a curve looks like. Thrust required with velocity. Alright. So this plot looks something like this. Okay. Now, where is the minimum thrust required? Minimum thrust required is somewhere over here. So this is the velocity at which L by D is maximum. Or this is the velocity at which thrust required is minimum. Alright. So this is the thrust required minimum. This is the thrust required minimum. And also remember thrust required was equal to what? Thrust required was equals to drag. So you can also mention this in this axis. We can also write drag over here. Okay. Fine. Now, how to find the point on this curve? Okay. How to find the point on this curve, or in other words, how to plot this curve thrust required with velocity. Alright. So there is a graphical approach for this. There is a graphical approach for this. What we do is, first we'll select some random velocity. Choose value of free stream velocity, V infinity. Alright. So once you have V infinity, then we can find the lift coefficient. Okay. And lift coefficient, remember what was the lift coefficient? CL equals to L by QS. Alright. And for steady level flight, we have lift equals to weight. CL equals to weight upon QS. Alright. What was Q? Q was half rho V square. So let me write here CL equals to 2W by rho S V square. Okay. CL equals to 2W by rho S V square. Now for the given aircraft, we know these values. We know the value of weight, velocity we just now assumed. We'll assume some altitude, maybe sea level altitude, where we have the given value of density 1.225 kilogram per meter cube. And given the aircraft, we also know the wing area. Alright. So now we have found the CL, and once we found CL, we can immediately find CD. Okay. So CD was CD naught plus KCL square. CD naught plus K is what? 1 by pi E AR. Okay. CL square by pi E AR. So given the drag polar, we will be having this value of CD naught and K. K is nothing but 1 by pi E AR. E is Ostwald efficiency factor. AR is the aspect ratio. Okay. So we are assuming the drag polar is known to us. Once we have CD, then we can immediately find what we are looking for. We are looking for L by D. We are looking for L by D. This L by D, CL by D or CL by CD. So once you have CL and CD, you can easily find what is CL by CD. Now once we have CL by CD, we were looking for what? We were looking for thrust required. Okay, we were looking for thrust required. So now we can calculate thrust required. That is TR. So TR is W by CL upon CD. So now we can plot. Then we plot thrust required with velocity. Okay, so we will also do it in a MATLAB example as well. We'll also be plotting in a MATLAB example as well using this graphical approach. Okay, so remember from where we started. For the graphical approach, we assumed the value of velocity, free stream velocity for a given aircraft. Then we were interested in finding out the lift coefficient, CL. CL equals to L by QS. For our steady level flight, it was lift equals to weight, and a dynamic pressure Q is given as Q equals to half rho V square. Alright. So once we have CL, and CL equals to 2W by rho S V square. So once we have CL, so we immediately find what is the drag coefficient. And the drag coefficient was given as CD equals to CD naught plus KCL square. CD naught plus CL square by pi EAR. So here we are assuming the drag polar is known to us. Okay. So the aircraft data, we have this information. Drag polar is known to us. Then we find CL by CD, that is the aerodynamic efficiency. And once we have CL by CD, then finally we can easily calculate thrust required. So thrust required equals to W upon CL by CD. Okay. Now we had considered only a single scalar velocity V infinity. So similarly for different velocities from this point to this point, we can easily plot. We can easily plot between thrust required with velocity in MATLAB. Okay, using this graphical approach. Alright, and this we'll also be doing in a MATLAB example. Okay, and we'll also discuss how the angle of attack is changing in this curve. Alright, how the angle of attack is changing in this curve. Okay, so let us quickly revise what we did in today's class. So first we did the MATLAB simulation for finding the pressure, temperature and density. Okay, then we shifted our focus now to flight mechanics. The basic concepts started from here, the equations of motion. I have drawn the free body diagram here, where we have I have introduced new angles, that is flight path angle and pitch angle, which I have explained over here. And using the equations of motion for the curvilinear motion and Newton's law, we have finally come up to these relations of thrust equals to drag and lift equals to weight. Okay, so always remember these are the equations for level unaccelerated flight. Thrust equals to drag and lift equals to weight. And then we came up to the relation of what should be the thrust required to maintain lift equals to weight. Okay, what should be the thrust required to maintain lift equals to weight. And as an engineer, we are interested in what is the minimum thrust required. For the minimum thrust required, the fuel efficiency will also be better. Alright, so we are interested in finding minimum thrust required. And thrust required minimum, we came to know it is applicable when L by D is maximum. So L by D is aerodynamic efficiency. Okay, so thrust required is minimum when CL by CD is maximum or L by D is maximum. And that L by D is maximum, that will correspond to the angle of attack at which thrust required is minimum, or angle of attack at which L by D is maximum, which is around 2 to 5 degrees. Okay, and then we started doing the graphical approach, how to plot this thrust required with velocity curve. Okay, so this is how we actually find the relation between thrust required and velocity using this graphical approach, and then we will also be plotting thrust required by velocity using some practical aircraft example. All right, so we'll continue from here in the next class. Thank you.